Hey everyone, and welcome back to my channel. In this video, we're going to dive into the exciting world of fine-tuning large language models, and specifically, we'll be looking at how to fine-tune the powerful Llama 2 model using a technique called LoRA, which stands for Low Rank Adaptation. Um, we're going to break down this Python code that I got going on here, and we'll go through it. This code is basically designed to take the pre-trained Llama 2 7B chat HF, which is this one right here, is a 7 billion parameter chat model, and adapt it to a specific style of conversation using a data set. So we're going to fine tune this, and basically fine tuning allows us to tailor these massive models to our own needs, making them more powerful. And LoRa is a super efficient way to do this without retaining the entire model, which basically saves us time and resources. So let's start from the top. Um, so the first section is all about installing the necessary libraries and whatnot. So you can see here we're using pip install -q to kind of quietly install these packages. Just to kind of go over some of these packages and stuff for you. So basically, um, this is the transformers. This is basically the powerhouse library from Hugging Face. It gives us access to pre-trained models like Llama 2, tokenizers, and all the tools we need to work with them. Datasets is also another Hugging Face library. Datasets basically helps us download and manage datasets for training and evaluations. Accelerate this library helps us speed up training, especially when we're using GPUs. So it's super helpful to kind of make things go faster. Torch, obviously, PyTorch is a deep learning framework and basically powers a lot of the stuff that we're doing. Um, Bits and bytes, this is a crucial library here. So it's basically for fine tuning, efficient fine tuning. You want to think of it like that. It allows us to load and work with models in a lower precision. And in our case, it's going to be an 8-bit precision, which basically what it does is saves memory um, and allows us to work with this model. Otherwise, it would be way too big. You're going to need so much GPU that you wouldn't be able to do this in Colab. All right, so the next thing here is we're installing um, bits and bytes. Uh, the, the, the we're using pip. We also want to make sure that we install the version of bits and bytes that's greater than 0.37.0, as the newer versions often have important updates and fixes. Okay, so next we load in our star of the show, which is the Llama 2 7B Chat HF model. In order to do that, first we need to log into Hugging Face. So I logged in here. You get your credentials from Hugging Face by creating it, and then when you put in this code, it's gonna ask you. Um, I guess I don't have it here. Once I already run, I'm not gonna run it again. But once you run this, it's gonna ask you for the code, and then you're just gonna uh, you know put it in, and it's like your Hugging Face token, and then you're gonna log in, and this gives you access to uh, the Llama 2 model. Now, this particular model, it is gated, so you do need to fill out a form on their on a website, and then it'll give you access to it. After some time, they'll review it. So that's what's called a gated model. So you don't have direct access to it right away. So you might have to do that first, then you can get that, then you can do this. Just to keep in mind. But once you do, then you can just log into Hugging Face, and then you'll get access to this gated model. And then you just hit run, log in, and that's it. That's all you need to do. So once you get in, these two lines are basically the magic here. So auto tokenizer and auto model for causal LLM are basically super convenient classes from transformers. They automatically detect and load the correct tokenizer and model architecture for MetaLlama uh, uh, the Llama 2 7B Chat HF model. So a tokenizer breaks down the text, just so you understand, like a tokenizer breaks down the text into smaller pieces called tokens that the model understands. And the causal, so the auto model causal LM loads the actual language model designed for tasks like text generation in our case. Causal language models like Llama 2 are all about predicting the next word in a sequence. Okay, so that's what a causal LLM is. So here we are. Let's kind of quickly also talk about tokenization a bit here. So okay, so we got the model in, and it takes a little time to load it, but okay, so let's talk about the understanding tokenization. So we give it, okay, let's take a particular prompt. Okay, we give it a prompt and say, what is the meaning of tensors? The tokenizer converts this text into numeral IDs, which are what the model processes. This is how it's able to process this sentence. You can see the output here in the dictionary, as you can see here, with so here we go. It's dictionary with input IDs and the attention mask. The input IDs are the numerical representation of our words. Okay. If we have multiple prompts, like in this case, where it's a dictionary of prompts in this example, then we use something called padding. And padding equal true makes all the input sequences the same length by adding special padding tokens. We set the tokenizer.pad token equals to tokenizer.eos underscore token to use the end of string token as padding, because sometimes these models, they don't actually come with a padding token, so we have to assign one manually. So that's why we do that over here. The attention mask is also very important. It tells the model to ignore these padding tokens during processing because they don't mean anything as far as like from like what we're trying to actually like encode and decode in our case. Like it doesn't have any meaning. It just is. It's a signal for the processing that's happening. So we don't want it to integrate in when we are encoding or decoding our response. Okay, so basically we tell it to ignore, and the attention mask, so that's why it's very important. It tells the model to ignore these padding tokens during processing. We don't want a model to learn from the padding. That's really the thing here. Okay. All right, so now that's what the output looks like. And finally, to see the model in action, we'll use a model.generate. We feed in our tokenized prompt, as you can see here, and tell to generate like 60 basically tokens. The output then is still in the token ID, so we use tokenizer.decode to convert it back into a readable text. As you can see, it's still in tokenizer, so we use this to decode it back, and then once it's decoded, you can see what the output is. This is the base Llama 2 model responding to our prompt, and this is before any fine-tuning. Okay, so now what we're going to do an 8-bit quantization of this model. Okay, so now let's talk about making this model more efficient. Llama 2 is a large model. Loading it in full 32 positions, which it comes out of the box, can be very memory intensive. In fact, I tried, and your entire Colab just crashes. So you definitely need to quantize this model, and so that's where 8-bit quantization comes in. Now you could do 4-bit quantization as well, but I tried with 4-bit and the responses were not so great when I was testing it. So I thought, and also I was still able to go up a bit, so and still be able to run it. So I thought, the closer you can be, the higher number you can be, the better. So in this case, we're doing 8-bit quantization. So how we do it is basically we create a bits and bytes config, and to load model the model in 8-bit. And we basically, that's where that comes in. It says load in 8-bit equals true. That's the key thing here. And then BNB underscore 4-bit underscore quanti type NF4, and other settings are basically, these are recommended configuration for 8-bit quantization, optimizing for performance and memory usage. Okay, so that's why we have those. And then as you can see here, 8-bit model is equals to autocausal LM for pre-train. We have our model right here, and then we do our quantization, and then we're end up with our 8-bit model right here. Okay. Now, just here we have here, just looking at the memory usage, just as a comparison. So for instance, this code calculates the estimated memory footprint. You can see that the dramatic reduction in memory usage when using 8-bit quantization. This is quite crucial because it allows us to fine-tune even on GPUs with limited memory. As you can see, difference, right? Look at 7 GB versus a memory footprint of 26 GB off of the 32-bit. Okay. And now what I just did here, I just wanted to see sort of what the output would look like for the 8-bit, and we can just like basically still, like we did before, just generate some text and see how it performs. As you can see, it's not too bad. It has the same question and it answers it pretty well. Not too bad, actually. Look at that. So I'm pretty happy with that. And so that's going to be our model that we're going to fine tune. All right, so now we're going to load in our data set. I'm getting the data set from Hugging Face. It's the human LLM/humans like DPO. You can look this up. It's yeah, I'll show you in a second what it actually looks like, but it's just straight out of Hugging Face. And this particular code is how you kind of grab it from Hugging Face. It makes it super easy. And we're going to store that as DS. And basically, this is a dictionary, and the features are there here, and it's all under train right now. So we're going to need to split that into train test validation in a second in order to do our training. And first thing we're going to do before we do that, we're going to convert this into a pandas data frame so we can manipulate it and do that kind of stuff that we want to do. Referring to the training test and validation data sets that we're going to create. And so here's the data set. It's got 3 features: prompt, chosen, rejected. The idea here is that you give it a particular prompt, and this is the ideal chosen response that you want the LLM to give. This is a rejected response. This is what the data set is based around. What we're going to do is we're just going to focus on these 2 features. And what I want to do actually is train the model to talk like this when you ask it any question. It's sort of like human with kind of an emoji kind of character personality to it, and so that's the idea here. And so that's the idea, just to kind of go down here and show you. So the before training, I'm taking the 8-bit model and I'm giving it this response, and this is the response that you get. Okay, it's not the best. It is an 8-bit model too. As you saw earlier, it gave a much better response over here. So when I gave it, okay, sorry. This is a different question than this, right? This is the what's the meaning of tensors. It's a little bit more straightforward of a question, and it give you this answer. This is, do you have a go-to karaoke jam? It's not, doesn't have much meaning to it as much, so it got a little confused. Anyway, this is the response that it's giving, and just to kind of give you an idea of what these features full look like, you can't really see it here. I kind of went over and give you, the first index of that data set. So here, I'm an artificial intelligence language model. I don't have personal experience. So this is the rejected, but we're not going to worry about that. In fact, we're going to get rid of it. As you can see here, we're going to get rid of it. This is the chosen data set based on the prompt. And what we want to train a model is to speak like this. Yeah, I've always been fascinated by music. I know the bus burst out. And this is number 4. So this is response to this. Do you have a secret talent or skill? And it's responding. Oops, I went too far. I've always been fascinated. So it's a very human-like. It's got emojis. It's kind of bubbly attitude. We're going to train the model to talk like this. Any question you give it. Okay. So this is the shape of it. And we're going to get rid of the rejected because we're not going to be working with it. So might as well get rid of it now. And this is where we are now with this. Okay. So we got 2 features in this data set and we're going to work with it. Now we're going to create the data for fine tuning. The way we're going to do that, we need to split it into training, validation, and test sets. And we use train test split from scikit-learn to create these sets. We first split off the test set, and then we split off the remaining data into the train and validation set. Having separated sets ensures that we can evaluate how well our model generates to unseen data. Okay. Next, we convert these into so this is what it looks like, as you can see here. Prompted. So that's our test train, and at one point I had the test as well. But yeah, that's what it looks like. Now what we're going to do here, anyway, if you were to put in the other ones, it would be the same thing. It's just different portions of the data set. Okay, and that's our training size, 7,622. Sorry, okay, and then validation is this much. Okay, now we're going to tokenize it. To tokenize that, we first convert these pandas data frames that we have back into dataset objects, because these are the format preferred by the Hugging Face libraries. So we create the dataset dictionary to organize our train, test, validation datasets. Okay. And now comes, so that's what it looks like. As you can see, these are dataset dictionary. And now here's where we're going to tokenize it, and this is quite important to look at. This is a crucial part. Tokenizing our data set for fine-tuning is very important, the way we do it. And let me give you an idea. So we defined this tokenized function, okay, and then we're going to run our data set through it. Okay, our basically our training and validation. Okay, so formatting conversations is quite important. So we iterate through. Let me just go through what's happening here. First, we iterate through the prompts and chosen responses. We format them using the Llama 2 chat template, which is basically this Llama 2 chat template looks like this. Okay. Next, we tokenize these formatted conversations using our tokenizer, and we set the padding equals the max length, and we want the truncation to be true because we do want to get truncate any. We want everything to be nice and square. So if there's area sentences and stuff that are long, we're gonna have truncation happening, and we're gonna set a max length of 512 so that all of the data sets have a max length of 512. Okay, so that they're all the same length and we don't exceed 512 and everything stays square, then we can train properly. This is where it gets a bit clever. We only want to train a model to generate the desired response, not necessarily like a learn the prompt. So we create labels. For the prompt part of the input, we set the label to -100. In PyTorch, -100 is a special value that tells the loss function to ignore these tokens during training. So, for the prompt part, we set all the input values to -100. For the desired response part, we use the actual token IDs as labels. This way, the model is only penalized for errors in generating the desired response. Okay? And then, finally, just like the input IDs, we pad the labels with -100 to ensure that they are the same length as the input IDs. And basically, we use dataset.map to basically map our dataset to this function that we have, tokenized function. Okay, we map every single line to it. And we apply it using this dataset.map function. And we also, what we do is we remove the original text column so that because we only really need the tokenized inputs and labels now. We don't need the old labels that were there before. And so we end up with this, essentially. Okay? And from here, you can kind of see like what the dataset train looks like, what the validation looks like, what the tokenized dataset on the first index of the data looks like. Isn't that cool? And so we're tokenized. We're ready to go here. So now we're gonna go into highlighting what happens in doing LoRa technique. Okay. So LoRa, or low rank adaptation, is a technique that allows us to efficiently fine-tune large language models by only training a small number of extra parameters. Instead of updating all the billions of parameters in Llama 2, LoRa basically adds small trainable modules so that we're going to be only training those. And I'll show you in a second a code that's going to demonstrate that. But let's just go into the code for a second here. So what we're doing here, just as to repeat, only training a small number of extra parameters. Okay. First, we install the PEF library. A lot of times Colab comes with it, but I like to just have it there anyway. And PEF basically stands for parameter efficient fine tuning. There's many different approaches, techniques to PEF. We're using LoRa specifically. Just keep that in mind. We're also gonna prepare our 8-bit model for LoRa training using this piece of code right here. This is some necessary adjustments to the model for compatibility with LoRa 8-bit quantization. Okay. And now we configure LoRa using LoRa config, and I'll go through what these lines mean. So R is basically this is called the rank of the LoRa matrices. Higher rank means more trainable parameters, but also more memory and potentially more fine-tuning capability. 8 is usually a pretty good starting point. The alpha is a scaling factor for the LoRa weights. The dropout is for regularization in the LoRa layers. We set the bias equal to none. We're not adding bias terms for this LoRa layers. It just helps with, again, the process that we're doing makes less memory and faster and all that stuff. So we're not adding bias terms to the LoRa layers. And the task type that we're selecting is a causal LLM because we specify that we're working on a causal language model. So we need to make sure that we give the task type as causal LLM. And then the target modules, this is quite important. Remember, we talked about earlier, we said LoRa adds small trainable modules. So basically, we're specifying which layers of the Llama 2 model we want to apply LoRa to. These common attention and feed-forward layers are what we're actually targeting in this case. And choosing the right target models is very important and for effective LoRa like fine-tuning. So in this case, we picked these. Okay, you could pick less of them, you can pick a few of them, you know what I mean? This is all experiment, you know, that's what you do. So finally, we create the PEFT model using get PEFT model, and we pass in our 8-bit model and the LoRa config, and this wraps into our original model with LoRa parameters. So now that we have our PEFT model, I'm going to show you what it looks like. This is what you got. We can see that we have the LoRa embeddings into it, as you can see here. Okay, so now what we're going to do is we're going to train the our model. Okay, I said here where we're going to basically push this model later on. But essentially, these are the parameters that I've decided. I've gone back and forth and tested, and I decided to stick with these. Although there's still a ton of room for improvement, I will not say that this is the best. But just for the sake of testing, I decided to stick with this. Now, this did take quite a long time for it to process, and well, we got something out of it, and it does work. And it was more for kind of a testing purposes to see how this process unfolds and see if it does work. And so after training, I also will look at this line of code, and it tells us what percentage of the parameters are going to be trainable parameters. We're using LoRa, so it's only training a portion of the parameters, and then basically the percentage, which is like 0.3. So essentially, we're not really training the entire model, right? We're only training a percentage, which is really interesting because you know, you'll see in a second that we get fairly decent results even with training such a small percentage of the parameters. And then we trained it, and I won't go into the whole process, but basically we pushed to the hub, and now what I did was I pulled the model back out. Basically, I fed in the tokenizer and the model, and this is the model. And now what we're going to do is we're going to use that same question that we asked earlier. What is the meaning of tensors? Just for the testing purposes. To see what kind of response we get. And as you can see here, now the response is very human-like. You know, tensors, they're like mathematical superheroes, but instead of saving the world, they help us understand the world better. Very, you know, I cut it off at 60 mathematically, so you probably could have said more if I really, you know, prompted to. I do wonder what it would say. Let's just say like 120. It would take a second to run this, but I would be curious to see what it would say if we kept let it keep going like that. Um, but that's just what's very interesting that you know we were able to take this very large model um, and use 8-bit quantization to make it more memory efficient, and then we only trained a very small portion of their parameters, and we're able to make it speak uh, and put out response in in this kind of way. So that's a fun little experiment to run and see how these things work. And if this thing loads, here's the 128 length response, and you can see here, like, it's got an emoji. It's like, in simple terms, the tensor is a mathematical object that can be used to describe a relationship between set of geometric. So as you can see, like, it's got its tone by basically fine tuned.